So every idea that is modeled with mathematical formula starts from a theory. Here I want to make a connection for you between the idea, the theory, and present very briefly the mathematical way to formalize that theory. And this is an idea that is used a lot in language technology. It appears a lot of places because it is a way to model the probability, which is very important to much of language technology. And the idea here comes from information theory. It's called the noisy channel. So one way you can think about this is to go back to, say, World War II when they had radio communication, walkie-talkies that were sent over radio waves. This is still true in theory. It's used in digital communication, but back then is when it first appeared because they had these walkie-talkies for the first time. And so the enemy figured out that there was important communication happening across the radio waves. And to block it, what they would do is just throw a jamming signal, which would be like a noise or a static over a bunch of radio frequencies so that they could just, a bunch of the channels that they might use would have these noise appearing that was messing up the signal. So if you were on one side receiving this message, right, and trying to hear um, what the people were saying and what message they were trying to send you, well, um, if you had this noise, it was going to be hard. So how are you going to figure out what what they were saying? Um, well, one way to do that would be to go back across the field and ask them, "What did you say?" But that would kind of defeat the purpose of the walkie-talkie. So the other way to do that would be to try to figure out what they are saying by eliminating the jamming signal. So instead of trying to figure out what the message was, you tried to figure out what's the jamming signal that the enemy is using and imitate it so that then you could eliminate it. You could eliminate the noise by figuring out what was causing the noise, by modeling that noisy channel. And then if you knew what was causing the noise, you could work backwards and get the message. So that's the noisy channel idea. Okay, so here we go, kind of laid out here. We have an actual signal, somebody saying something, or somebody's trying to spell something, type something, and this, yeah, this could be walkie-talkie saying something, or it could be speech recognition. This is actually where it got started. It was first applied to speech recognition. So we didn't look at it when we looked at speech recognition, but now we're looking at it, and you'll see it appear again, like in machine translation, same idea here, that there's a message or a signal that needs to get across, whether that's they're trying to spell something, you're trying to say something, or you're trying to say something in one language and it's being received on the other end in some sort of distortion. So uh, we don't hear it correctly, or actually the speech technology just can't really hear it as well as human ears. So we treat it as a distortion, or it is actually misspelled, which is a distortion, or we treat French as some sort of distorted English. So if we are receiving French or trying to receive French, if we could work backwards to figure out what this distorted English is, or what is causing the distortion, then we might be able to figure out a way to translate between the languages. So what is this channel that makes this distortion from English to distorted English, which is actually French? But in spelling, it's a bit more clear, right? There's actual distortion that happened between what our fingers meant to type and what they actually typed. Well, we don't know what that actual signal is. The computer doesn't know. We might be able to guess, but computers can't guess. They don't have world knowledge. So the goal is to recover the actual signal, the intended word, from what we actually see. And we do that by modeling distortion. So we try to figure out what that distortion is or what it's most likely to be. So that's like trying to figure out what the jamming signal is, what that frequency is that they're sending over all those waves, so that then when you process the message, you can eliminate that noise and hopefully get from backwards to the original intended signal. So we're working backwards because we have to work with what we observe, which is going to be what the computer processes or what the misspelling is. Okay, so that's the theory here. So in specifically in misspelling and spell checking, we can think about it this way. There is some correct spelling X. We can't observe it. We don't know what it is. The computer can't even guess looking at it and say, oh, yeah, most people would spell this way. It doesn't have that world knowledge. All it has is the misspelling. So we want to recover the correct spelling X from the misspelling. So some important terminology here that we're going to start with an example and keep in mind what these things are. So this Y, this misspelling, is our observation. This is our data that we have that we actually observe. So in other words, it's the incorrect spelling or that word that was distorted somehow, if we think about it as a distortion because there was some noise that was thrown in the middle. We want to figure out what was the spelling error. We want to recover from that misspelling. If we can figure out what the error was and we can model it, that's our noisy channel, then we should be able to eliminate the error or work backwards and figure out what the correct word was supposed to be. So we do that with probability. We don't know exactly, we can only guess, but intelligent guessing is working on probability and statistics. So we're going to find the X, that is the correct spelling, that yields the highest probability given the misspelling. So in other words, if we go through all the possible correct spelling and we calculate the probability of somebody making an error that would get them from the correct spelling X to this misspelling, that's our noisy channel, what is the most probable spelling error? Or what is the most probable, working backwards, what is the most probable of all the possible words, correct words, what is the most probable word given that all we can observe is a misspelling? And that's our noisy channel, right? We don't know what the intended spelling is. It could be multiple possible misspellings if you have a lot of words that are only one letter apart. So let's try to figure out not what's the most likely word, correct spelling, what's the most likely spelling error. So we formalize that by saying a conditional probability. If we assume out of all, we start with one word that could be from the dictionary. If we assume that the correct spelling is X, what's the probability that this spelling error would get us from the misspelling back to X? So what's the probability of X given that the misspelling is Y? It's working backwards, it's a little bit confusing, and we don't think through this when we see a misspelling such as this, right? Donald with that. Right? We can look at that and be like, oh yeah, well, world knowledge tells me that's probably Donald, the name Donald. The computer doesn't know it. Computer has to work this out without any world knowledge. So it doesn't know what the intended spelling is, and it doesn't know what the misspelling is because it doesn't know what the intended spelling was. So we have to recover the correct spelling from this misspelling, working backwards. Now, you could go through all the possibilities, right? Now, you could keep this simple and say, okay, let's only look at all the words that are one edit distance away. That simplifies it. And then we could go further and say, well, let's only look at the letters in the two that are different. So let's look at all the words that are one edit distance away. Honestly, I don't know of any other words besides Donald that would be one edit distance away, so that keeps it easy. But let's say there is a real word. Maybe let's say there's a real word here. Uh, let's say Donald, like that. Oh, I don't know why it disappeared like that. That's very interesting. Let me try that again. Oh, okay, here we go. All right, let's just say that's a real word. So we have another candidate for the computer because if it's only one option, we could just choose that. But if we don't, we have to figure out what's the most probable correct spelling. Well, in this case, it would be their misspelling was caused by not a transposition of the DNL, but a insertion, right? We got from Donald without the D to Donald by inserting the D. That's one edit distance. Okay, so which one is the correct one? Well, in a spell checker, we're going to provide both. So really, we're asking ourselves, which one do we want to rank the highest? Which one is the most probable? And if we do this correctly, and we compare the probability of insertion versus the probability of transposition, which is the only two options we have, hopefully, given a well, we'll talk about that in a second, but a good spelling checker is going to come up with, the most probable spelling error here is transposition. So therefore, I'm going to yield Donald as the highest ranked over Donal, uh, because that is the X that is most probable given all the possible spelling errors that we tried. So we're going to try all the different spelling errors, and one of them is going to be more probable than the other, and so it's going to give us a correct spelling, or in this case, uh, not necessarily, we don't know for sure it's correct, but one of them is more probable, so we rank it higher. All right. So going over the same thing here, we're just working backwards. And we're trying to get this idea of noisy channel and connect it to this formalism here of the probability of Donald given the misspelling. But we'd also have to figure out what's the probability of Donal given the misspelling. And the one that we would rank the highest is the one that yielded the highest number from those two. So the most probable or maximized probability is the one that we say is the best model of that noisy channel. This is most likely the jamming signal, the frequency that that enemy machine is spitting out. So let's try to then mimic it, eliminate it from the channel, and that should get us the original message that we wanted to hear. So that's the idea. The noisy channel it seems pretty basic. But like I said, what we want to do here is not just start with a basic idea, but start to connect it to the formalism, the mathematical models. And so the first thing that you can note here is that the noisy channel model is a kind of Bayesian inference. And I'm not going to go into definition of what that is. I could do that. I could just ignore these terminology and say, don't worry about it, you understand the idea. But I don't feel like that's going to be helpful for you if you take this into other classes. So I want to go ahead and make this really brief connection to the formalisms. So first of all, Bayesian inference. So it's a way of getting at probabilities with what's called Bayesian inference, which means that we use Bayes' theorem or Bayes' rule. And there's going to be a video on Bayes' rules, but I'm going to go ahead and make another jump, which to say in language technology, we do a simplification of Bayes' theorem or Bayes' rules, and it's called naive Bayes. And if you pay attention, you'll note the difference between Bayes and naive Bayes is that down here, there's no denominator. There's no something under there, which makes it simpler to do the math, which is nice. So it turns out very nicely that in language technology and in AI in general, this naive Bayes works just as well. So for pragmatic reasons, it's very nice for us to be able to use a simpler version of Bayes' theorem. So we won't worry about the more complex, although you'll watch a video that shows just the general idea of why this whole idea of Bayes' theorem or Bayesian inference can be useful in the world. Okay, so let me just make this quick connection between that noisy channel and the formalisms here. Hopefully I can make this clear. So remember that we were trying to get at X, which is the original signal, the correct word, from what we actually have, which is the misspelling. So we want to know what is X given Y, right? That's put here. What is the correct word given that we've seen a misspelling? But it's really impossible to calculate directly. We don't know what the person intended to spell. We don't know what the correct word is. And I mean, obviously we picked an easy one where Donald is kind of only one choice there. Like I said, I don't know another word in English that has a one uh, is similar to it or could be misspelled. Maybe you guys can think of one. So that one's easy, but in most cases, it's not that easy. In most cases, there are many possible X's. So trying to figure out here which one is correct by we're going to end up guessing. We can't calculate directly because we can't read the speller's mind. We don't know what the person sending the signal over the walkie-talkie meant to say. If we did, why would we bother with walkie-talkies at all? So instead, we have to work backwards. What we can calculate from what we have, okay, so down here's the formula, and I'm going to just show you the connections between the ideas in the formula really quickly. What we can calculate, or what we have, is observation. So we have Y. So we can figure out the probability of the misspelling if we assume that we know what X is. So that means we can go to all the possible X's. So Donald and our other one that we mentioned, Donal, and we can say, let's assume that X is Donal, and what's the probability of, again, what's the probability of insertion? It was probably that they accidentally inserted a D, okay? And we can do the same with Donald. What's the probability that there was a transposition of these two letters? And we've got two there that we can compare. So um, generally speaking, how you do this is you want to go through all the possible words. That's your X, and do this for each of them. So that's probability of the misspelling giving all possible words. So we'll go through each one of those X's and we'll look at the confusion matrix and we'll say, okay, well, what happened here? Well, they inserted a D. Okay, well, we've got a matrix of all the counts of all the times that people accidentally type a D after an A. And the other option, Donald, that's a transposition. Okay, well, our confusion matrix, all the times that D and L are transposed with each other. So actually, if you think about it, we actually have to figure out this probability. So there's a probability inside a probability. These things get complex, but that's what Y is telling us. What's the likelihood? So Y there is actually, okay, what's the likelihood that people are going to insert D after an A? And we then figure out the conditional probability, which we won't go into, but that's the thing we can figure out, right? Because we have those two pieces of information. So that's this part right here. We can figure that out based on what you have. We don't have to read the speller's mind, the typer's mind. And then the other thing that we do have is to figure out X. What's the probability of the correct word or any of the possible words occurring in a text, right? That's our context, the English text. So we're asking, okay, right? We went through and we assumed that X was Donald, assuming this is a real word in English. Write that again. And we looked at the probability of people inserting a D. What's the probability of the misspelling? Then we asked the same thing with Donald. What's the probability, if we assume that the correct word is Donald, what's the probability of a transposition? Okay, what if they end up to be the same? That's possible. So very nicely, we can use this information here, the probability of the correct word occurring in the text. So then we can do counts of all the times and all the data we have that Donald occurs and all the times that Donald occurs. And we'll take that and we'll divide it by the total number of names or whatever, right? That's going back to our probability. We do the counting, we divide by the context that's relevant. And that will give us a probability of Donald occurring, probability of Donald occurring. So we can take then the probability that the D was inserted before the L. So the probability that Donald is correct, given, or assuming Donald is correct, what's the probability of that misspelling mistake, that confusion happening, times the probability of Donald occurring at all. And we do the same thing with Donald, then we compare and we get a probability, and then we're going to rank the one with the highest number higher than the other. So just real quickly here, you can see why probabilities get to be called weights sometimes, because when you put them together in this multiplication, for example, it might be that the probability over here of inserting a D, given Donald is the correct one, right? That's what we're assuming, is the same as the probability of transposing D and L, right? When we assume that Donald is the correct one. But and I'm sure this is true, if Donald is a much more common name that occurs in English text, it's going to weight, right? It's going to kind of pool the probability towards a higher number than Donald, which is going to be a smaller number, right? It's going to not pool it as hard. So that's just how multiplication works. So if you have a really high number, Donald's just much more frequent. It's going to weight it. And then that probability, once we multiply, becomes a weight. And so that's why we use those terms of weight, probability, likelihood in different contexts. Okay, that was a little bit extra there for you. But it's kind of cool to think about how these all get plugged together into something more complex. And this is actually a simple example, right? With language technology, it gets much more complex. But again, just like with probabilities, this is a simple idea. And if you can understand the simple idea and hopefully make some connection to the formalisms here, then really the rest of it is just doing a bunch of these rather simple things and just doing a bunch of layers on them and multiplying them. So you can understand the basic idea no matter how complex language technology and AI get, which is really, really great.